Resistivity logs contain an SP or gamma ray curve on the left side of the log display. The resistivity curves scaled in ohms, or more precisely ohm meters, are on the right-hand side of the log, commonly on a logarithmic scale. There are several types of resistivity logs in use today. This is a common type of resistivity log, the dual induction log. Although recorded on a scale up to 2,000 ohms, our curves on this example are displayed on a scale from 0.2 ohms up to only 20 ohms. The dashed curve is a record of the induction log deep device, or ILD, which is designed to read the true resistivity, R sub T, of the uninvaded zone. The dotted curve records the induction log medium device, ILM, which generally measures the resistivity of the transition zone. The dual induction log is commonly run together with a log that has a shallow depth of investigation. In this example, a spherically focused log, SFL, displayed by the solid curve, serves this purpose. The SFL log records resistivities that are strongly influenced by the flushed zone, R sub XO, adjacent to the borehole wall. At the top of the sand, as determined by the SP curve, we see a higher resistive zone, overlying a low resistive interval. At an initial glance, this appears to record high resistivity hydrocarbon overlaying lower resistivity formation water. To confirm this interpretation, we need to know if the resistive interval is porous, because the resistivity could be caused by a tight, low porosity sand. Now let's add a porosity log to the display. In this case, the combination neutron density log that we examined earlier. We recall that the dashed neutron curve and the solid density curve read apparent sandstone porosity. Our high resistivity sand is obviously porous, because the neutron and density curves show from 17% to 38% porosity throughout most of the interval. We also recall that separation of the porosity curves, as we see here, with the neutron curve reading low porosity and the density reading high porosity, indicates the presence of gas. A term, R sub WA, is used to indicate an apparent formation water resistivity. In the case where water saturation is assumed to be 100%, the Archie water saturation equation can be written as the apparent water saturation, R sub WA, equals the true resistivity of the formation, R sub T, over the formation factor, F. If we assume that the deep induction log curve records the resistivity of the uninvaded zone, we can replace R sub T in our formula with ILD, the value of the deep induction curve. It should be emphasized that R sub WA is only equal to the true resistivity of the formation water, R sub W, when the formation is 100% water saturated, as we see here. Thus, in hydrocarbon-bearing formations, the calculated apparent water resistivity, R sub WA, will be greater than the true water resistivity, R sub W. Going back over our equation, then, R sub WA is obtained simply by dividing the deep induction resistivity by the formation factor, F. Let's return to the log of our South Louisiana sand. First, we obtain the R sub WA for the portion of our sand which is 100% water wet. We identify such a zone here at 12,445 feet, as revealed by the low resistivity readings. Before we calculate the R sub WA, we must first establish a value for F, the formation factor. You'll recall that for sandstones, the formation factor equals approximately 0.81 over the square of the porosity. We thus square the log porosity of 30% and divide it into 0.81. Our formation factor, then, is 9. Now, to find the R sub WA of the water-wet sand, we simply divide the formation factor 9 into 0.4 ohms, the induction log deep reading obtained from the dashed curve. Our R sub WA then becomes 0.04 ohms. Since we determined this value in a 100% water-wet formation, where R sub W is equal to R sub WA, we now have established a value for R sub W as 0.04. The R sub WA in the resistive hydrocarbon-bearing zone at the top of the sand, here at 12,384 feet, is then calculated. We recall that earlier we calculated a porosity here of 30.4%, which is approximately midway between the neutron and density porosity readings. Thus, to obtain the formation factor F, we again divide the sandstone factor, 0.81, by the square of the porosity, 0.304, which equals 8.77. At 12,384 feet, the deep induction curve reads about 12 ohms. Our R sub WA is then obtained by dividing the induction log deep reading of 12 ohms by the formation factor, 8.77, which gives us an R sub WA of 1.37. To obtain the water saturation, S sub W, of a zone, we take the square root of the water resistivity, R sub W, divided by the apparent water resistivity, R sub WA. Thus, the water saturation at 12,384 feet equals the square root of 0.04 divided by 1.37, which equals 17%. Hence, our gas saturation at this depth equals 83%. An R sub WA value can be continuously calculated by a computer during the log run and displayed as a curve on the left-hand side of the log. The R sub WA scale on our South Louisiana log is from 0 to 0.5 ohms, with a backup scale of 0 to 5 ohms when the curve goes off scale. Opposite the water-filled sand at 12,245 feet, the computed R sub WA is close to the R sub WA of 0.04 ohms that we calculated manually. A rule of thumb is that an R sub WA value at least 3 times that of the true water resistivity, R sub W, indicates probable hydrocarbon pay. In the case of our South Louisiana sand, we thus look for R sub WA values over 0.12 ohms, which is 3 times the R sub W value of 0.04. On this basis, we have pay from 12,376 feet to a gas-water contact at 12,408 feet and a net pay of 30 feet.